When a really heavy star runs out of fuel at the end of its life, it begins to collapse under the sheer force of its own gravity. If that star was between 10 to 25 times the mass of the Sun, then what's left over is a really dense ball of neutrons called a neutron star. And if the star's even heavier, then the collapse continues all the way down to a single point in space. And what we're left with is something called a black hole, a region of space-time where gravity is so strong that not even light can escape. Most black holes are between 5 to 100 times the mass of the Sun when they form. But in the centre of every galaxy is a supermassive black hole, an object with a mass of more than 1 million suns, which acts like the galaxy's engine, powering its evolution over billions of years. Now, the universe itself has actually only been around for 13.8 billion years, and it turns out that that's not enough time for supermassive black holes to grow just by gobbling up all the surrounding matter, like stars and interstellar gas. So how did they get so big? Now, one possibility is that supermassive black holes formed as pairs of smaller black holes were pulled in towards each other and eventually merged. Now, as a black hole pair is spinning, it produces ripples in the fabric of space-time called gravitational waves. And for pairs of really big black holes, these gravitational waves can be as long as an entire galaxy. So to detect them, what we need to do is look for really bright objects in the sky, which is spread out like a kind of galactic measuring stick. And here at Jodrell Bank, scientists are looking at objects just like this called pulsars, which are a type of neutron star.
So pulsars are exotic stars. They are the size of a city, they weigh as much as the Sun, and they can spin around as fast as your kitchen blender. As they spin, beams of radio waves shoot out from the poles of the pulsar, and as the poles pass over the Earth, we see flashes that are like ticks from a cosmic clock. The rotation of pulsars is extremely stable, so we can measure subtle variations in these ticks to tell us about gravitational waves that are passing over the Earth.
When a gravitational wave passes through these pulses, it can actually cause them to arrive earlier or later, and if we measure those delays, we can actually measure the gravitational wave themselves. So these intense beams of light from pulsars are actually in form of a radio wave. So we need a radio telescope to detect them.
At Jodrell Bank, we have the Lovell telescope, which was the world's first giant dish, but is still doing cutting-edge pulsar science today. Combined with colleagues all across Europe, we can observe hundreds of these pulsars, and by putting that data together, we're able to detect subtle gravitational wave signals that we think are coming from many supermassive black hole binaries spread all through the universe. By observing these gravitational waves, we will learn about the mysterious origins of supermassive black holes and of the galaxies in which they live.